That empty blackness between the stars is secretly building everything. The universe's greatest illusion is that nothing is truly empty. And today you will understand how the void crafts reality itself. We are going to journey to the edge of modern physics, where scientists have discovered that the vacuum of space is not a barren nothingness but a seething, dynamic sea of potential. You will see how this fundamental emptiness gives rise to every galaxy, every star, and even life. We will uncover how particles blink into existence from pure emptiness, and how the entire cosmos may have erupted from a single quantum fluctuation. This knowledge will permanently shift your perception of reality. What does the idea of a creative, living nothingness make you feel? Our everyday idea of emptiness is a profound illusion. We look up at the night sky and see a silent, black void between the stars, but this is a trick of our limited perception. The truth is far stranger. That apparent nothingness is, in fact, a vibrant arena of constant creation and destruction. This concept is not entirely new. Over 2,000 years ago, the Greek philosopher Democritus argued that everything is made of atoms and void. He believed the void, the empty space, was just as necessary as the atoms themselves, providing the stage upon which reality could unfold. Yet even he could not have guessed just how active that stage truly is. Modern physics has torn down the classical idea of a passive vacuum. We now know that what we call empty space is saturated with what is known as the zero-point energy field. Think of it not as a still pond, but as a restless ocean, its surface constantly churned by a quantum storm. At the tiniest scales, pairs of particles and their antiparticles are continuously blinking into existence, borrowing energy from the universe for an unimaginably brief moment before annihilating each other and vanishing back into the background hum. These are called virtual particles, and their fleeting dance is proof that the void is not empty. It is a seething sea of potential, a foam of probabilistic energy. This zero-point energy is the universe's lowest possible energy state, a fundamental background hum that can never be switched off, not even at absolute zero. This means true, absolute nothingness, a state of zero energy and zero activity, may not actually exist anywhere in the cosmos. The very foundation of our universe is built upon this dynamic, energetic void. It is from this restless quantum sea that the first whispers of everything emerged. This endless quantum churn is governed by a rule so fundamental it reshapes our idea of reality. It is called Heisenberg's uncertainty principle, and it states, in essence, that the universe is built on a foundation of fuzziness. At the subatomic level, you can never precisely know both the exact position and the exact energy of a particle at the same time. The more you pin down one, the less you know about the other. This is not a limitation of our machines, but a basic feature of the cosmos. It means that on the smallest scales, empty space cannot simply be still and have zero energy. For a tiny sliver of time, energy can seemingly appear out of nowhere, borrowing against the cosmic ledger to manifest as pairs of particles and their antiparticles. They exist for a fleeting moment, a ghostly dance of creation and immediate annihilation before vanishing back into the void. These are not just mathematical tricks. They are real events with real consequences, and we can even measure the subtle push they exert, an effect known as the Casimir Force. If you place two incredibly smooth metal plates extremely close together in a vacuum, the sheer number of virtual particles that can exist in the open space outside the plates is greater than the restricted types that can fit between them. This imbalance creates a faint but measurable pressure that pushes the plates together, a direct physical proof of the quantum, sees restless activity. So, where does this lead us? These quantum fluctuations were the original seeds. In the first instance of the universe, during a period of hyper-fast expansion we call cosmic inflation, these microscopic ripples in the fabric of spacetime were stretched to astronomical sizes. The tiny, random variations in density born from the quantum foam became the gravitational blueprint for everything to come. The slightly denser regions began to pull in more matter, eventually collapsing into the vast cosmic webs of galaxies, stars, and planets we see today. The grand structure of our entire observable universe, with its billions of galaxies, was imprinted by these random whispers from the void. The great cosmic stage was set by the smallest of actors, appearing from what we mistakenly call nothing. This ultimate cosmic event, the Big Bang, presents us with the most profound puzzle of all. How could everything we see, the entire universe, emerge from a state that appears to be nothing? The Big Bang theory describes the hot, dense beginning of our cosmos, but it leaves a more fundamental question unanswered. What was the initial trigger? What set the whole process in motion? Leading cosmological models point us back to the quantum void we just explored. The prevailing idea is that our entire universe could be the result of a single, monumental quantum fluctuation. In the grand scheme of things, a universe might be the ultimate virtual particle, blinking into existence from a pre-existing, timeless void. This concept is deeply tied to a state known as the false vacuum. Imagine a universe not in its most stable, lowest energy state, but trapped in a kind of cosmic metastability. Think of a ball resting precariously on the peak of a very steep hill. This is the false vacuum, a state of high energy that is temporarily stable but ultimately unstable. All it takes is one tiny nudge, one quantum fluctuation, for that ball to roll down into the true valley below, which represents the lower, stable energy state of our current vacuum. That transition, that roll downhill, would release an unimaginable amount of energy, triggering a period of hyper-fast expansion we call cosmic inflation. In a fraction of a second, a quantum speck smaller than a single atom was inflated to a size larger than our entire observable universe. But this leads us to the most mind-bending question of all. What existed before the Big Bang? The most startling answer from modern physics is that the question itself may be meaningless. Time, as we understand it, may have begun with the Big Bang. Asking what came before the start of time is like asking what is north of the North Pole. The singularity from which our universe erupted may represent the absolute beginning of spacetime itself. So the Big Bang was not an explosion in a pre-existing space, but the rapid emergence of space and time from a state of pure potentiality, a quantum fluctuation in the ultimate void. This is the universe's greatest illusion made real on the grandest possible scale. The aftermath of this incredible event set the stage for the universe we know today. This period of inflation was a moment of such extreme transformation that it defies all everyday intuition. The universe did not simply expand at a steady pace. It underwent a runaway growth spurt, doubling in size over and over again in intervals so brief they are almost impossible to describe. In a span of time far less than a blink of an eye, a region of space smaller than a single proton was stretched to a size larger than our entire observable universe. This explosive stretching is the crucial link that takes the microscopic quantum seeds we discussed and magnifies them into the cosmic architecture we see in the night sky. Without it, those tiny fluctuations would have remained just that tiny. Inflation took those random whispers from the quantum foam and blew them up to an astronomical scale, imprinting them across the entire cosmos. This process also solved two of the universe's great mysteries in one go. First, it explains why the universe appears so remarkably uniform in every direction we look, the cosmic microwave background revealing a nearly perfect temperature across the sky. Any initial irregularities or clumps were stretched so thin by inflation that the universe was ironed smooth, like pulling on a wrinkled sheet until it becomes flat and even. Second, it explains why the geometry of our universe appears so perfectly flat, a delicate balance between expansion and gravity that seems too perfect to be coincidence. Inflation stretched the fabric of space itself to such an incredible degree that any initial curvature was flattened out, just as inflating a balloon makes its surface appear flatter and flatter from the perspective of a tiny ant crawling on it. But what was the engine for this incredible growth? The driving force is thought to be a scalar field, often called the Inflaton field, which permeated all of space. Think of this field like an invisible mist filling the early cosmos, a mist trapped in a state of incredibly high energy. This high energy state acted like a form of anti-gravity, pushing space apart at an ever-accelerating rate. As this field very slowly relaxed, losing its pent-up energy, that energy was not lost. It was transformed, flooding the universe with a hot soup of particles and radiation, effectively creating all the matter and energy we know from the potential energy of the field itself. This is the ultimate act of cosmic alchemy, where the potential of a field, a form of structured nothingness, is converted into the substance of everything. The slightly denser regions in the quantum foam, now stretched to vast scales by inflation, became the gravitational anchors for the future. After inflation ended and the universe settled into a more sedate expansion, gravity began to pull on these subtle density differences. Over hundreds of millions of years, the slightly denser patches pulled in more and more matter, eventually collapsing under their own weight to form the first protogalaxies and then the stars within them. The stage was now set for the next great act, the forging of the first elements from the primordial fire. Out of that furious expansion, a new reality began to cool. The universe was no longer a singularity, but it was still an unimaginably dense and hot firestorm, a primordial soup of pure, radiant energy. Within this seething chaos, the first tangible building blocks of everything were about to be forged. This is the moment where energy began its great transformation into matter, a process governed by the most famous equation in all of science. You have heard of E equals mc squared, but it is far more than a formula on a page. It is the universe's own recipe for creation, a direct statement that energy and mass are two sides of the same coin. The speed of light, c, is an enormous number, and when you square it, it becomes a colossal conversion factor. This means a tiny amount of mass holds a staggering amount of energy, and conversely, a vast amount of energy can condense into a tiny speck of mass. In the intense heat of the early universe, this was not a theoretical idea. It was happening everywhere continuously. Pairs of particles and their antiparticles were spontaneously crystallizing out of the energetic background, born directly from the fury of light itself. The first actors to emerge from this sea of energy were the most fundamental particles we know, quarks, the restless building blocks of protons and neutrons. Electrons, the nimble particles that would one day orbit atomic nuclei, and elusive neutrinos, ghostly particles that barely interact with anything, streaming through the cosmos by the trillions every second. For a fleeting moment, the quarks and the particles that bind them, called gluons, were not confined within larger structures. They existed in a state known as a quark-gluon plasma, a kind of ultimate subatomic soup where individual particles roamed freely. But as the universe expanded and cooled further, a critical change occurred. The temperature dropped just enough for the strong nuclear force to take hold, acting like a powerful glue that permanently bound trios of quarks together. This was the birth of the first protons and neutrons, the heavy cores of all future atoms. Think of it like water vapor cooling and condensing into droplets. The radiant energy of the early cosmos was cooling, and as it did, it condensed into the first solid, massive particles. This was the ultimate materialization, the point where the energetic void gave rise to tangible substance. The universe was no longer just a flash of light. It now had something to build with, but these particles were still just a chaotic, seething cloud. For the universe to become structured, another monumental shift was required, one that would see these raw ingredients assemble into the first true atoms. So with the first particles now forged, what is the deeper reality they exist within? To answer that, we must step beyond the idea of solid little balls and into a far more fluid and fundamental concept. The universe at its heart is not made of particles at all. It is made of fields. Quantum fields are the true, invisible architects of everything. Picture an infinite, invisible ocean that fills every cubic centimeter of the cosmos, a seamless medium that exists even in what we call empty space. This is not just one ocean, but a whole family of them, one for each type of fundamental particle. There is an electron field, a quark field, a neutrino field, and more, all overlapping and permeating all of reality. According to quantum field theory, what we perceive as a particle is merely a localized excitation, a tiny vibration or ripple in its corresponding field. An electron is not a tiny speck moving through emptiness. It is a knot of energy, a gentle hum in the universal electron field. A photon, a particle of light, is a wave rippling through the electromagnetic field. This perspective completely flips our intuition. The fields are the primary, eternal substance of the universe. The particles we see are temporary manifestations, like temporary peaks on the surface of a vast and deep sea. This explains the bizarre behavior of quantum mechanics, where particles can act like waves and pop in and out of existence. They are not solid objects appearing and vanishing. They are excitations rising from and settling back into their underlying fields. The void, the vacuum of space, is simply the ground state of all these fields. It is the calmest, lowest energy configuration they can have. But as we have seen, this calm is an illusion. The ground state is not zero. It is a seething foam of potential, where virtual particles constantly flicker as the fields quiver with residual energy. One field in particular plays a starring role in giving the universe its substance, the Higgs field. Imagine this field as a kind of invisible, cosmic molasses that fills all of space. Most fundamental particles, like quarks and electrons, interact with this Higgs field as they move. This interaction is what we experience as mass. A particle that interacts strongly with the Higgs field feels more drag, becoming heavier. A particle like a photon, which does not interact with the Higgs field at all, remains massless and zips through the cosmos at the speed of light. Without this field, there would be no atoms, no planets, no us. Everything would be ethereal, massless energy, flashing through the universe at light speed without ever coalescing into stable structures. The Higgs field is the cosmic sculptor that gave matter its weight and its form. Yet the most profound connection lies in the nature of empty space itself. If the vacuum is the ground state of these quantum fields, and those fields are not nothing but possess a fundamental energy, then empty space itself has weight. This is the stunning revelation that brings us back to the greatest cosmic mystery of our time, dark energy. The energy of the vacuum, the energy of the quantum fields in their ground state, appears to be the most likely candidate for the force that is accelerating the expansion of the universe. So the same quantum fields that weave the fabric of reality from apparent nothingness are also, through their inherent vacuum energy, dictating the ultimate fate of the cosmos. This mysterious force, dark energy, is the modern echo of the creative void we have been exploring. It is the dominant component of our universe, making up about 68% of everything, and its sole effect is to push the cosmos apart at an ever-increasing rate. This is not the gentle, coasting expansion from the Big Bang's initial push. This is an acceleration, as if space itself is being stretched from within. The gravity generated by dark energy is not attractive like the gravity from matter. It is repulsive. Think of it this way. The gravity from planets and stars pulls things together, acting like a brake on the universe's expansion. Dark energy, in contrast, acts like an accelerator, pressing down on the cosmic pedal and forcing galaxies to flee from one another faster and faster as time goes on. The most compelling clue to its identity lies in its behavior. The energy density of dark energy appears to be constant. As the universe expands and grows more vast, this strange energy does not thin out. More space simply means more dark energy. This points directly to a stunning possibility. Dark energy might be an intrinsic property of empty space itself, a concept Einstein first conceived of as the cosmological constant. He initially introduced this idea as a sort of fudge factor to keep his equations describing a static universe, later calling it his greatest blunder when the universe was found to be expanding. Yet today it may be his greatest vindication. This cosmological constant could be the energy of the quantum vacuum we discussed earlier, the seething zero-point energy of all those quantum fields in their ground state. If this is true, then the same quantum foam that gave rise to particles and galaxies is now, through its sheer pervasive presence, governing the ultimate fate of the cosmos. The nothingness is not just a stage, it is an active participant, its hidden energy now writing the final chapters of the universal story. As this accelerating expansion continues, it dictates the future of the cosmic structures we see around us. This grand cosmic architecture did not assemble by chance. The distribution of galaxies across the sky reveals a pattern of breathtaking complexity and order, a vast cosmic web of glittering filaments and immense dark voids. This sprawling structure, the largest known pattern in nature, has its blueprint written in the first moments of time, traced back to those faint quantum ripples in the primordial void. Those microscopic density variations, stretched to astronomical proportions by inflation, became the gravitational anchors for everything to come. In the early universe, these regions of slightly higher density held an invisible advantage. They were permeated by dark matter, a mysterious substance that does not emit or absorb light, but whose gravitational pull is the primary architect of cosmic structure. Think of dark matter as the invisible skeleton of the universe. It collapsed first, forming a vast, intricate scaffold under the influence of gravity. The slightly denser knots in this dark matter web began to pull in the normal matter, the hydrogen and helium gas forged in the Big Bang. As this gas flowed along the dark matter filaments, it cooled and condensed, eventually igniting into the first stars and coalescing into the first galaxies. We can now map this cosmic web with stunning precision. Immense surveys like the Sloan Digital Sky Survey have charted the positions of millions of galaxies, revealing a universe structured like a neural network or a froth of soap bubbles, with galaxies clustered along the walls of immense voids. These voids are not entirely empty, but they are the deserts of the cosmos, regions where the gravitational pull was too weak to gather matter. The entire arrangement, from the largest supercluster to the smallest dwarf galaxy, is a direct consequence of the initial conditions imprinted by quantum mechanics. Those random whispers from the quantum foam were amplified into the gravitational tides that shaped the cosmos. This structure is more than just a beautiful pattern. It is the necessary cradle for life. Within the dense clusters and along the rich filaments, galaxies collide and merge, triggering new waves of star formation and scattering the heavy elements like carbon and oxygen forged in stellar furnaces. These elements, the very stuff of planets and life, were seeded throughout the cosmic web, eventually finding their way into nebulae and planetary systems. The existence of this intricate architecture, born from quantum uncertainty, provided the stable, resource-rich environments where solar systems could form and life could potentially arise. The void did not just create matter, it organized it. It wove a web of such grandeur that it could ultimately support conscious beings capable of looking back and tracing their own origin to a fleeting tremor in nothingness. This fine-tuning of the cosmos raises a profound and unsettling question. Why does our universe possess such a precise set of rules, a collection of fundamental constants and forces that seem perfectly calibrated for complexity and life? If the force of gravity were even slightly stronger, the universe would have collapsed back on itself immediately after the Big Bang. If it were slightly weaker, matter would never have clumped together to form the first stars. The strength of the nuclear forces, the mass of the electron, the exact value of the cosmological constant, each one appears balanced on a razor's edge. This remarkable observation is known as the Anthropic Principle, a concept that bridges physics and philosophy. The weak Anthropic Principle offers a straightforward, almost tautological explanation. It states that we can only observe a universe that is capable of supporting our existence as conscious observers. In an unimaginably vast and varied cosmos, or even a multiverse, we inevitably find ourselves in one of the rare, hospitable pockets where the conditions are just right. This is a selection effect, not a grand design. Imagine a puddle of water waking up one morning and thinking, "This hole I am lying in fits me perfectly. It must have been made precisely for me." The puddle does not realize it has simply adapted to the shape of the hole. In this view, we are that puddle, and our universe is the hole we happen to find ourselves in. The strong Anthropic Principle takes a much more speculative and controversial step. It suggests that the universe must, in some sense, have properties that allow life to develop within it at some stage in its history. This version hints at a deeper, underlying reason for the fine-tuning, perhaps even a form of teleology or purpose woven into the fabric of physical law. The most compelling scientific framework for the weak Anthropic Principle is the multiverse. If our cosmos is just one bubble in an infinite froth of universes, each with its own random set of physical constants, then the mystery vanishes. In the overwhelming majority of these universes, the numbers would not line up. There would be no atoms, no chemistry, no stars, and no one to ask why. We simply live in the one universe where the lottery numbers came up right. This idea pushes the concept of a creative void to its absolute limit. The quantum fluctuation that gave rise to our universe was not a singular, special event, but one of countless such events in a greater meta-reality, a vast and eternal landscape of nothingness giving birth to everything over and over again. So was our universe with its illusion of something from nothing, a random accident. Or is the existence of conscious observers like ourselves a fundamental part of the cosmic equation, a necessary feature that the laws of physics must accommodate? This question does not yet have a scientific answer, but it forces us to confront the staggering possibility that our own awareness might be an inextricable part of the reality we seek to understand. This brings us to a final, dizzying frontier, the connection between the cosmos and the mind itself. Does the universe exist in a definite state, waiting to be discovered, or does our act of observation somehow complete it? Quantum mechanics forces this very question upon us. At the heart of this mystery is the observer effect, a phenomenon where the simple act of measuring a quantum system seems to force it to choose a single, concrete reality. Before measurement, particles like electrons do not have a definite position or state. They exist as a cloud of probabilities, a superposition of all possible locations and conditions at once, described by a mathematical entity called the wave function. It is only when a measurement is taken that this wave function appears to collapse, and the particle snaps into a specific, measurable state. The most famous illustration of this is the thought experiment of Schrödinger's cat, where a cat in a box is considered simultaneously alive and dead until someone looks inside, collapsing its fuzzy quantum state into one definite outcome. This leads to a deep and unresolved puzzle. What exactly constitutes a measurement? Is it the interaction with a machine, or does it require something more, a conscious awareness to finally crystallize possibility into actuality? The traditional Copenhagen interpretation of quantum mechanics sidesteps the question of consciousness, stating that the wave function collapses upon interaction with a macroscopic, classical measuring device. In this view, the universe is divided into a quantum realm of potential and a classical world of definite facts, and the boundary between them is where reality becomes fixed. Yet, this has never been a fully satisfying answer. It simply pushes the question back a step, asking when a collection of atoms becomes classical enough to cause a collapse. This ambiguity opens the door to a far more radical possibility, that consciousness itself is the fundamental agent that transforms the quantum void's infinite potential into the solid world we experience. Could it be that the universe only becomes concretely real when it is observed by a conscious mind? This idea suggests that the void's creative power is not complete without a witness. The quantum field may generate the possibilities, the probabilities, but it is perception that selects the single timeline we call reality. We are not passive inhabitants of a pre-built cosmos. We may be active participants in its continuous creation, our awareness acting as the final brushstroke that paints the definite world onto the canvas of potential. This blurs the line between physics and philosophy, challenging our most basic assumptions about what is real and what is illusion. If consciousness is indeed a fundamental part of the cosmic equation, then the greatest trick the void ever pulled was not just creating everything from nothing, but creating the observers necessary to give that everything meaning. The solidity of the desk in front of you, the tangible weight of your own body, these may be the most convincing illusions of all. A revolutionary idea emerging from the edges of black hole physics and string theory proposes that our universe of 3 dimensions might be a hologram, a magnificent projection from a 2-dimensional surface at the very edge of reality. This is known as the Holographic Principle. It began with a profound puzzle about black holes. When matter falls into a black hole, it seems to vanish, taking all its information with it. This violates a core tenet of quantum mechanics, which states that information can never be truly destroyed. The resolution, discovered by physicist Jacob Bekenstein and later expanded by Leonard Susskind, was as elegant as it was bizarre. They realized that all the information describing the matter that fell into the black hole is not lost inside the inaccessible singularity. Instead, it is perfectly encoded and stored on the black hole's event horizon, the 2-dimensional boundary from which not even light can escape. The event horizon acts like a cosmic hard drive, with each tiny plank-sized area storing a single bit of information. The mind-bending leap was to ask, if this is true for a black hole, could it be true for the entire universe? Could the three-dimensional space we inhabit, with its galaxies, stars, and planets, be a projection from a distant, two-dimensional surface that encloses us? In this model, the world is akin to a financial hologram on your credit card. The flat, shiny surface contains all the information needed to project a seemingly three-dimensional image. You are not looking at a flat picture, you are experiencing a projection of depth. In the cosmic version, the fundamental building blocks of reality are not particles or fields, but bits of information. The universe is not made of stuff, it is made of data. Every particle interaction, every force, every event that unfolds within the volume of space is a translation of information processed on its boundary. This redefines the nature of the void we have been exploring. That apparent nothingness is not a seething quantum foam, but a vast, information-rich surface, a cosmic film on which the entire movie of our reality is written. The solid world we experience is a decoded message, an incredibly complex and convincing rendering generated from a simpler, lower-dimensional reality. If this is true, then the ultimate nothing is not an empty void, but a blank slate, a surface waiting to be written upon. The transition from nothing to everything is not a material creation, but a computational one, a thought that leads us directly to the next great frontier. This idea that the universe is a projection of information leads us to an even more radical proposition. What if reality is not just described by information, but is literally made of it? What if the cosmos is not a physical object, but a colossal computation in progress? This is the core of digital physics, a view that reimagines the very substance of existence. The pioneering physicist John Wheeler coined the phrase "it from bit" to capture this concept. He proposed that every particle, every force field, every occurrence in the universe ultimately derives its existence from binary answers to yes or no questions. In this framework, the bedrock of reality is not matter or energy, but bits of information. An electron is not a tiny speck, it is a localized bundle of data. A gravitational field is not a curvature in space, but a flowing stream of information processing. The universe, then, is not a thing that computes, it is the computation. This perspective finds a startling echo in the work of Konrad Zuse, the German engineer who built the first programmable computer. He was one of the first to seriously suggest that the entire cosmos might be running on a cellular automaton, a vast cosmic grid where simple rules, applied over and over, generate the breathtaking complexity we see around us. Think of Conway's Game of Life, a simple digital simulation where cells on a grid turn on or off based on the state of their neighbors. From a handful of basic rules, intricate, moving patterns emerge that seem almost alive. Now, imagine that our universe is a version of this game, but with quantum rules and trillions upon trillions of dimensions. The galaxies, the stars, and you yourself would be unthinkably complex patterns emerging from the relentless execution of a fundamental code. This transforms our understanding of the creative void. The nothing from which everything emerged is no longer a seething quantum field, but the blank initial state of a cosmic processor, the pristine condition before the first line of code was executed. The Big Bang was not an explosion of matter, but the moment the universal program booted up. The laws of physics are not mysterious decrees, but the immutable algorithms of this grand computation. This forces a profound question about the nature of existence. If the universe is a computation, who or what is the programmer? The answer from digital physics is both humbling and awe-inspiring. The programmer might be no one. The universe could be a self-contained mathematical structure, a set of abstract relations that simply are, and our perceived reality is just our limited perspective from within that structure. In this view, the universe is not a simulation running on some alien supercomputer in a higher reality. It is that computer, and its hardware is the very fabric of space-time. This pushes us to the final, most abstract frontier of all, where we must ask if reality is ultimately made of mathematics itself. This final abstraction dissolves the very idea of a computer, leaving only the pure language of mathematics itself. If reality is a computation, then its fundamental code must be written in the only universal language we know, the language of numbers, sets, and equations. This leads to the mathematical universe hypothesis, a proposition so profound it challenges the bedrock of what we consider real. Proposed by physicist Max Tegmark, it states that our physical world is not merely described by mathematics, which is undeniable, but that it is mathematics. In this view, a mathematical structure and a physical reality are one and the same thing. Think of the number pi. It has an infinite, non-repeating sequence of digits. It exists as a perfect, abstract concept. It does not need a universe to exist in. Its properties are true regardless. Tegmark suggests that all such consistent mathematical structures exist in a kind of Platonic realm of perfect forms. Our universe, with all its galaxies, forces, and particles, is not a unique creation. It is simply one particular, incredibly complex mathematical structure that we happen to inhabit. The matter you are made of, the space you occupy, are not primary. They are emergent properties of a deeper, abstract relational network. So what, then, is the ultimate nothing from which this mathematical universe sprang? It is not an empty void or a silent processor. It is the complete set of all possible self-consistent mathematical structures, an abstract landscape of every possible universe that could logically exist. Our cosmos is not a special creation, but one equation that, in a sense, solved itself into existence. This reframes the most fundamental question in all of science. Are the laws of physics something we discover, like explorers charting a pre-existing continent? Or are they something we invent, like artists imposing a pattern on chaos? The mathematical universe hypothesis argues forcefully for discovery. The laws are not flexible rules that a creator chose. They are immutable truths, the necessary logical relations within the specific mathematical structure we call home. We are not inventing the rules of chess as we play. We are slowly, painstakingly, learning the rules of the game that has already been set. This idea is not just philosophical speculation. We may be able to test it. The bizarre behavior of quantum particles, which exist in multiple states at once until measured, finds a natural home in this framework. A particle's wave function is not a physical field, but a mathematical description of probability. Its collapse into a single state is not a physical event, but the updating of information within the structure. The famous double-slit experiment, where a single electron seems to pass through two holes at once, makes perfect sense if the electron is not a tiny ball, but a solution to a wave equation. The physicality we experience, the solid desk, the warmth of the sun, becomes the grand illusion. They are not the foundation of reality, but a user interface our brains have evolved to interpret the underlying mathematical code. The universe's greatest trick was not creating something from nothing, but convincing us that the abstract, weightless world of numbers is solid. But do these ideas remain trapped in the realm of abstract theory? The answer is a resounding no, for we can witness the void's creative power right here on Earth, inside some of the world's most sophisticated laboratories. The most direct physical proof comes from a subtle yet measurable force. Picture two perfectly smooth, uncharged metal plates placed incredibly close together in an absolute vacuum, so close they are almost touching. According to classical physics, with no electric or magnetic fields between them, nothing should happen. Yet, the plates are gently pulled together by an invisible hand. This is the Casimir effect, and it is a direct signature of the quantum sea's restless activity. The space outside the plates is vast, allowing for virtual particles of all wavelengths to blink in and out of existence. The narrow gap between the plates, however, is so small that it restricts which wavelengths can form, with more quantum activity pushing on the plates from the outside than from the inside. The net result is a faint but definite pressure that squeezes them together. We are literally measuring the pressure of nothingness. Even more compelling is a dynamic version of this experiment. By vibrating one of these mirrors at nearly the speed of light, scientists can actually pluck real particles from the void. This is the dynamic Casimir effect. The rapid motion acts like a cosmic paddle, churning the quantum foam with such violence that virtual particle pairs are shaken apart before they can annihilate. The virtual particles are converted into real, detectable photons of light, literally creating something from nothing. We are not just observing the vacuum's activity, we are actively harvesting its potential. On an even grander scale, particle accelerators like the Large Hadron Collider perform this alchemy constantly. When they smash protons together at velocities approaching light speed, they are not breaking solid matter into smaller pieces. They are concentrating immense energy into a tiny point, recreating the conditions of the early universe. In that microscopic fireball, pure energy spontaneously condenses into a shower of new particles and their antiparticles, materializing directly from the collision's fury. This is E equals mc squared in action, a direct demonstration that energy and mass are interchangeable currencies. These experiments are not metaphors. They are tangible, repeatable evidence that the void is a generative medium. The quantum fields that fill empty space are not passive backdrops, they are the source. What we see in these laboratory moments is a microscopic echo of the universe's own genesis, a fleeting glimpse of the process that built everything from the ground up. This empirical foundation allows us to look at the cosmos with new eyes, confident that the principles at work in our machines are the very same ones that orchestrated the birth of galaxies. Our universe may be just one page in an infinite cosmic library. This is the multiverse, a concept that stretches the idea of creation from nothing to its absolute limit. The first compelling version arises from our own cosmic story. We discussed the period of inflation that blew up our universe, but what if that inflation never truly stopped? In a model called eternal inflation, the rapid expansion is a runaway process. Most of this meta-space is still inflating at an unimaginable rate, but in random locations, the inflationary energy decays like a bubble forming in a boiling pot of water. Each of these bubbles is a universe cooling and forming its own distinct reality, with its own laws and constants, forever separated from our own by the ever-expanding, inflating space between them. In this view, our entire cosmos is just one bubble among an infinite froth of others. A second, equally profound version emerges from the quantum world. The many worlds interpretation takes the wave function of quantum mechanics at face value. It says that every time a quantum event has multiple possible outcomes, the universe does not choose. Instead, it splits, dividing into branches where every possibility is realized. In one branch of reality, you are listening to this, while in another, you decided to do something else moments ago. This is not a metaphor, but a proposed physical reality where an uncountable number of parallel worlds are constantly branching off from every quantum decision. The third grand vision comes from string theory, which suggests that the fundamental constants of physics are not absolute, but are determined by the way extra, hidden dimensions of space are curled up. This theory describes a landscape of possible vacuum states, a vast collection of different ways for a universe to be stable. Each of these 10 to the 500 possible configurations represents a different universe with different particles and forces. In this landscape, our universe is just one possible valley among a near infinity of others. So what does this mean for our original question? The nothingness that gave rise to our universe is not a special, one-time event. It is a common, even mundane, occurrence in a meta-reality where new universes are constantly being born, either from the quantum foam of a parent cosmos or from the sheer, unadulterated potential of mathematical consistency. The canvas of creation has expanded beyond a single masterpiece to an endless gallery of every possible reality. The ancient Greeks were the first to wrestle seriously with the idea of nothing. Parmenides, a philosopher from the 5th century before the Common Era, made a startling declaration. He argued that nothingness cannot exist, and that to speak of it is to speak of nonsense. For him, reality was a single, unchanging, eternal plenum, a fullness where true emptiness was a logical impossibility. This was a profound rejection of the void. Yet his own student, Zeno, created his famous paradoxes, like the arrow that never reaches its target, to defend this very idea, showing that the concepts of motion and change led to absurd conclusions if one denied a fundamental unity. But other Greek thinkers pushed back. The atomists Leucippus and Democritus boldly claimed that reality was composed of only two things, atoms and the void. For them, the void, the kenon, was not nothing. It was an infinite, featureless space, a necessary stage that allowed atoms to move and interact. Without this void, they reasoned, the atoms would have no room to maneuver, and the cosmos would be a frozen, solid block. This was the first great philosophical schism, a debate between a universe of pure being and a universe of being and non-being, a debate that would echo for millennia. This intellectual journey through nothingness did not end with the ancients. The German philosopher Martin Heidegger in the 20th century brought the question to a deeply personal level. He asked, why is there something rather than nothing? This was not a scientific query for him, but a profound existential one. He explored the concept of das Nichts, the nothing, not as an empty container but as the very ground of our being. For Heidegger, our acute awareness of the possibility of nothingness, the anxiety we feel in the face of our own mortality, and the potential non-existence of the world, is what reveals the startling fact that there is something. We only understand what it means to be because we can confront the terrifying possibility of not being. This philosophical nothing is a far cry from a simple scientific vacuum. It is a fundamental mood, a background hum of anxiety that defines the human condition and makes the existence of everything seem so startling and precious. So how does this abstract, philosophical nothing compare to the physicist's vacuum? The philosophical absolute nothing would be a state of no space, no time, no quantum fields, no laws of physics, and no potential for anything to ever arise. It is the utter and complete absence of existence in any form. The scientific vacuum, as we have explored, is nothing like this. It is a rich, structured something, a bubbling quantum sea governed by the strict laws of quantum field theory and general relativity. It has energy, it fluctuates, and it has a specific structure. Calling the quantum vacuum nothing is a dramatic misnomer from a philosophical standpoint. It is, in fact, a very particular kind of something, the lowest energy state of a set of fields within an existing spacetime. This forces a difficult question. Is the philosopher's absolute nothing even a coherent concept? Could such a state ever logically exist? Some argue that the question itself is a category error, a trick of language. We are using a word, nothing, to try to describe a state that by definition has no properties and cannot be described or even conceived of without turning it into a something in our minds. The moment you ask what nothing is, you have given it a property, the property of being an object of inquiry, and it ceases to be nothing. This rich history of thought does not invalidate the scientific quest. Instead, it deepens it. The philosopher's struggle to define nothingness highlights the sheer strangeness of the physicist's discovery that the closest thing we can find to nothing is a vibrant, generative plenum. It bridges the abstract terror of the void with the concrete, measurable reality of the Casimir effect and virtual particles. Understanding this intellectual journey allows us to see the scientific puzzle not just as a technical problem, but as the latest chapter in humanity's oldest and most profound conversation. We are still asking the same question Parmenides and Heidegger asked, but now we have powerful new tools to probe the answer. This fusion of abstract thought and empirical discovery brings us to the final, sobering implication of a creative void, forcing us to confront what its inherent energy means for the ultimate fate of every galaxy, every star, and every atom. This relentless expansion, driven by the void's own dark energy, charts a course for a deeply unsettling final act. The ultimate fate of our universe, according to our best models, is not a fiery collapse but a slow, cold whisper into silence, an era cosmologists call the heat death or the big freeze. Picture the cosmic story not as a cycle but as a single, one-way journey for all energy. The universe is like a wound-up clock, full of concentrated, usable energy in its youth, but it is steadily and irreversibly running down. Every star is a temporary reservoir of that energy, but they are all slowly burning out. Trillions of years from now, the last stars will have consumed their fuel, their fiery hearts extinguished, leaving behind cold, dark cinders like black dwarfs, neutron stars, and the frozen remnants of planets. Even the mightiest structures, the galaxies themselves, will have drifted so far apart in the expanding void that their lights will no longer be visible to one another. The cosmos will become a much lonelier, much darker place, but the decay goes deeper than starlight. Even the seemingly permanent remnants will not last. Through a process predicted by Stephen Hawking, black holes themselves are not eternal. They slowly leak radiation, losing mass over incomprehensible timescales until they, too, evaporate in a final, faint puff of particles. On even longer timescales, the very protons and neutrons that form the bedrock of all atoms may themselves be unstable, decaying into pure energy. What remains after all of this? A universe that has reached a state of maximum entropy. This is a term for the ultimate level of disorder, where all energy has been evenly spread out. No more hot spots, no more cold spots, no more gradients to drive any process. It becomes a vast, static, and profoundly dark sea of ultra-low energy photons and other fundamental particles, so thinly spread and so low in energy that they effectively never interact again. This is the cosmic equilibrium, a state of effective nothingness. The vibrant, structured cosmos we know will have returned to a near-featureless void, a chilling echo of the quantum sea from which it first emerged. This linear view of time, from a creative void to a final, silent one, forces a deeply philosophical confrontation. If everything ultimately fades to black, what does that mean for the meaning we find in existence? Is the universe's grand story just a temporary, brilliant flicker in an eternal night, a fleeting pattern that the void allowed to form before settling back into stillness? Or does the sheer fact that consciousness and beauty could arise from the laws of physics, even for a cosmic instant, impart its own enduring significance? The journey from nothing to everything and back again may be the most fundamental rhythm of reality, leaving us to wonder if the silence at the end is truly an ending or just the void waiting to speak again. Even the darkest prisons in the cosmos are not immune to the creative whisper of the void. Stephen Hawking revealed that black holes, long thought to be the ultimate endpoints of existence, are not truly black. They glow, they radiate, and they slowly evaporate, all thanks to a delicate quantum dance at the precipice of their event horizons. This process, now known as Hawking radiation, begins with the same virtual particle pairs we have discussed, those fleeting fluctuations in the quantum field. Normally, these particle-antiparticle pairs annihilate each other almost instantly, returning their borrowed energy to the vacuum. But something extraordinary happens when this dance occurs right at the edge of a black hole's point of no return. In that region of incredibly warped space-time, one of the virtual particles can be tugged by the black hole's immense gravity, falling across the event horizon while its partner is flung outward, escaping into the universe. This is not a simple separation. The escaping particle does not get a free ride. For it to become a real particle, it must steal its energy from somewhere. That energy is taken directly from the black hole's own mass. The particle that falls in has negative energy relative to the outside universe, and when it crosses the horizon, it effectively reduces the black hole's total mass and energy. So, from the perspective of a distant observer, the black hole has just emitted a particle, glowing faintly with a temperature inversely proportional to its size. The smaller the black hole, the hotter it glows and the faster it evaporates. Over astronomical timescales, this slow but steady trickle of radiation means that even the mightiest black holes will eventually shrink and vanish, returning their substance back to the universe. Hawking radiation is a stunning synthesis of seemingly irreconcilable theories. It weaves together the large-scale gravity of general relativity with the tiny-scale uncertainty of quantum mechanics, and it even introduced thermodynamics to black hole physics, giving them a definable temperature and entropy. This single idea shatters the classical view of black holes as eternal, inescapable prisons. They are not static graves for matter and light, but dynamic, evolving objects that participate in the universe's cycle of creation and decay. The most hostile environments imaginable are still governed by the same quantum rules that allow something to emerge from the gravitational energy of nothing. This staggering mismatch between prediction and observation is the vacuum catastrophe, a problem so severe it threatens to tear modern physics apart at the seams. The numbers involved are almost impossible to grasp. When physicists calculate the energy density of the quantum vacuum using our best theory of the small quantum field theory, they arrive at an astronomically huge figure. This is the sum of all that zero-point energy from the ceaseless churn of virtual particles. Yet, when we measure the energy density of empty space through its effect on cosmic expansion, the value we get from dark energy is incredibly, bafflingly small. The theoretical prediction overshoots the real, observed value by a factor of 1 followed by 120 zeros. To put that incomprehensible error into perspective, it is the difference between predicting an ocean that fills the entire observable universe and measuring a single drop of water. This is not a minor rounding error. It is the most spectacular failure of a scientific prediction in all of human history. The catastrophe reveals a terrifying chasm in our understanding. Either our mathematics for the quantum world is profoundly wrong in a way we cannot see, or there exists a miraculous, perfectly tuned cancellation mechanism that almost but not completely zeroes out this titanic vacuum energy, leaving behind the faint whisper we call dark energy. The implications are staggering. If the quantum field theory calculation were correct, the repulsive force of the vacuum would have been so immense that it would have ripped apart every atom, star, and galaxy before any of them could even form. The universe would be a featureless, expanding void, utterly sterile and devoid of structure. The fact that we exist to ponder this problem means that the vacuum energy is, for some reason, almost exactly zero. This fine-tuning is so precise it seems to defy all odds, pointing either to a hidden natural principle or to the unsettling possibility that our universe is unnaturally, perfectly balanced for life. Resolving this catastrophe is the holy grail of theoretical physics. It is the essential bridge we must build to unite quantum mechanics with general relativity into a single, coherent theory of quantum gravity. Until we understand why the energy of nothing is so close to nothing, we cannot claim to truly understand the engine behind the cosmos's greatest illusion. These vibrating strings are the universe's ultimate soloists, playing every note in the cosmic symphony. String theory asks us to forget the idea of tiny, solid dots as the foundation of matter. Instead, it suggests that the most basic building blocks of everything are unimaginably small, one-dimensional loops or strands of pure energy. Their different vibrational patterns, their unique frequencies and harmonies, are what we detect as different particles. One specific vibration might manifest as an electron, while another, more complex resonance becomes a quark. In this view, the entire zoo of subatomic particles is not a collection of different things, but different songs played on the same fundamental instrument. This simple, elegant shift in perspective has a breathtaking consequence. It forces us to rewrite our understanding of the stage itself, the void where this music plays. For the mathematics of string theory to work, to produce all the forces and particles we observe, the universe cannot have only the three spatial dimensions we experience. It requires more. The theory suggests there are at least 6 additional spatial dimensions, all curled up and compactified into shapes so incredibly tiny that they are hidden from our perception, existing at the Planck scale. This is the true nature of the vacuum in this framework. What we call empty space is not an empty box. It is an intricate, dynamic geometric structure, a hidden multidimensional landscape of breathtaking complexity. Primary candidates for these hidden shapes are known as Calabi-Yau manifolds. These are not shapes you can easily picture. They are complex, multi-dimensional forms with intricate holes and tunnels, a kind of topological lacework that defines the properties of our reality. The specific way a Calabi-Yau manifold is folded and curled determines the resonant frequencies available to the strings vibrating within it. In a very real sense, the geometry of this hidden world dictates the laws of physics in our visible one. It decides the mass of the electron, the strength of gravity, and the number of particle families. To complete this radical picture, we must introduce brains. Short for membranes, these are multidimensional objects that can exist within the higher dimensional space predicted by string theory. Our entire universe, with its 3 dimensions of space and 1 of time, could be a vast 3-dimensional brain floating within a higher dimensional bulk. All the matter and forces we know, with the possible exception of gravity, could be confined to this brain, like images trapped on the surface of a soap bubble. This would explain why we are utterly unaware of the extra dimensions. We are stuck on our own cosmic slice of reality. Gravity, however, being a manifestation of space-time geometry itself, could leak between brains, which might explain why it is so weak compared to the other fundamental forces. So the ultimate nothing in string theory is this vibrant, multidimensional void, a geometric arena of hidden dimensions and vibrating strings. The everything we see and are is simply the rich spectrum of music emerging from this hidden architecture. This is the theory's grand promise, a single, unified description of all forces, from the quantum dance of atoms to the cosmic pull of gravity, all born from the resonant vibrations of a hidden, geometric void. But what if the very stage of reality, the fabric of space and time, is not a smooth, continuous sheet? Loop quantum gravity offers a radically different vision, suggesting that space-time itself is woven from individual threads. This theory proposes that space is not infinitely divisible. It is grainy, composed of tiny, discrete loops, the true atoms of space. Picture the universe not as a blank canvas, but as an incredibly fine, shimmering tapestry, with each fundamental thread a billion times smaller than a single atom. The vacuum, the void we have been exploring, is therefore not an empty container. It is this dynamic, evolving network of fundamental excitations, a web of relationships where each loop carries a tiny, quantized unit of area and volume. The smooth, continuous space we move through is an illusion of scale. Much like a television screen appears as a seamless image until you get close enough to see the individual pixels. This granular structure resolves a central conflict in modern physics. General relativity describes gravity as the curvature of a smooth space-time, while quantum mechanics governs a jittery, probabilistic world. Loop quantum gravity brings them together by making space-time itself inherently quantum. In this view, gravity is not a force propagating through space. It is a manifestation of the changing geometry of this spin network, a direct result of how these tiny loops connect and interact. This leads to one of the most profound implications of the theory, a complete avoidance of the gravitational singularity at the Big Bang. Instead of a point of infinite density where all laws of physics break down, loop quantum gravity suggests a big bounce. Our universe may not have been born from nothing, but could have rebounded from the collapse of a previous cosmic cycle. As that prior universe contracted, the density of the quantum spacetime fabric would have reached a maximum, causing a tremendous repulsive force to kick in, triggering the expansion we see today. The universe's beginning was not a singular creation from nothing, but a transformation, a phase change in the eternal, quantized fabric of reality. This theory provides a completely new perspective on the geometry of nothingness. The void is not a passive emptiness, but an active, woven structure. The stage upon which the cosmic drama plays out is not a given. It is built from the bottom up by the quantum connections between these fundamental loops of space. It is a vision where the architecture of reality emerges from the relationships between nothings, a cosmic tapestry forever weaving itself into existence. This paradox strikes at the very heart of our physical laws. When any object, whether a book or a star, falls into a black hole, it carries with it a vast amount of information. This is not just digital data, but the complete specification of every particle, its position, its spin, its quantum state. The fundamental rules of quantum mechanics are built on the principle that this information is never, ever lost. It can be scrambled, transformed, or hidden, but it cannot be erased from the universe. A black hole, however, presents a terrifying challenge to this sacred rule. From our perspective outside the event horizon, the point of no return, the object is gone, seemingly erased from existence. If the black hole then evaporates over eons through Hawking radiation, and that radiation is purely thermal, carrying no information about what fell in, then the information is truly destroyed. The universe would have a permanent case of amnesia, and our most trusted laws of physics would be fundamentally wrong. This is the black hole information paradox, a crisis that has divided physicists for decades. One of the most compelling solutions brings us back to the holographic principle. The information is not lost inside the singularity. Instead, it is perfectly and flawlessly encoded on the surface of the event horizon, the black hole's two-dimensional boundary. Every bit of data that falls in is imprinted onto this spherical surface, like a cosmic fingerprint pressed into the fabric of space-time. The three-dimensional reality of the falling object is translated into a two-dimensional description on the horizon's surface. The black hole's interior, then, might be a projection, a holographic reconstruction generated from that data on the boundary. This would mean the information never actually enters the black hole in a way that it can be destroyed. It is stored safely on the surface, and as the black hole evaporates, this information can be slowly and complexly released back into the universe through subtle correlations in the Hawking radiation. It would not be a clean, readable message, but the information would, in principle, be preserved. This leads to a staggering implication about the nature of reality itself. If a three-dimensional object can be completely described by information stored on a two-dimensional surface, then what we perceive as solid, voluminous reality might be a kind of illusion. The true, fundamental reality could be playing out on a distant, lower-dimensional screen. This forces us to ask what is more real, the object or the information that defines it. Is a tree defined by its wood and leaves, or by the intricate quantum information describing the arrangement of every atom within it? The information paradox suggests that the particles and the energy are secondary. The primary substance of the universe may be abstract, immaterial data. The void, then, is not a chaotic emptiness, but the ultimate information processor, a cosmic memory that never forgets, ensuring that the essence of everything that ever was or ever will be is eternally preserved. That perfect symmetry of the early cosmos could not last. Our universe began as a state of unimaginable unity, a realm where the four fundamental forces we know today, gravity, electromagnetism, and the strong and weak nuclear forces, were fused into a single, perfect symmetry. In that searing, nascent moment, there was no distinction between them. They were one and the same, a unified superforce. But as the universe expanded and cooled, it underwent a series of profound shifts, much like water freezing into ice. With each drop in temperature, a phase transition occurred and a fundamental symmetry was broken. Think of a hot, featureless mist cooling. As it does, intricate ice crystals begin to form, each one breaking the perfect rotational symmetry of the vapor by choosing a specific, unique orientation for its structure. The universe did the very same thing. In its first split second, the force of gravity may have been the first to peel away. Then, as the cosmos cooled further, the strong nuclear force, which binds atomic nuclei together, broke free from the electroweak force. The final major break happened next. The electroweak force, which had unified electromagnetism, and the weak nuclear force, itself shattered. This crucial breaking is where the world we recognize truly began to take shape, and it is governed by a process intimately tied to the Higgs field. Before this break, particles like the W and Z bosons, which mediate the weak force, and the photon, carrier of light, were all massless and indistinguishable in the symmetric state. They were different facets of the same gem, but as the universe crossed a critical energy threshold, the Higgs field underwent a dramatic change. It shifted from a symmetric state of high energy to an asymmetric state of lower energy, a process called spontaneous symmetry breaking. Imagine a ball balanced perfectly on the peak of a sombrero. This is the symmetric, high-energy state. The slightest nudge, however, will cause the ball to roll down into the hat's brim, a lower energy state that is no longer symmetric, as the ball has now chosen one specific point on the rim. The Higgs field did exactly this. It settled into a specific value throughout all of space, and in doing so, it broke the electroweak symmetry. This single event had a monumental consequence. Particles moving through this now constant Higgs field experienced different levels of interaction. Some, like the W and Z bosons, interacted strongly, acquiring significant mass. Others, like the photon, did not interact at all, remaining massless and traveling at the speed of light. This is why we have heavy particles that form matter and massless light that allows us to see. The diversity of our reality, the very existence of atoms, stars, and planets, hinges on this broken symmetry. Without it, everything would be an ethereal, weightless blur, a universe of pure light with no solid structure. Symmetry breaking is the cosmic sculptor that carved the rich, asymmetric world we know from the bland, homogeneous perfection of the primordial void. It is the hidden mechanism that translated the boundless potential of a symmetric beginning into the tangible, complex, and beautifully imperfect reality we call home. This line of reasoning leads to one of the most unsettling paradoxes in all of cosmology. The Boltzmann brain thought experiment pushes the idea of a creative void to its absolute logical limit. If the universe can arise from a random quantum fluctuation, and if the cosmos is vast and eternal, then we must consider what is statistically more probable. The formation of an entire, ordered universe spanning billions of years with galaxies, planets, and a continuous history of life is an event of incredibly low probability. In contrast, the spontaneous fluctuation of a single, self-aware brain, complete with all its senses and a fully formed but entirely false set of memories, would be far more likely. This disembodied consciousness would pop into existence for just a moment, believing itself to be a person with a past, living in a real world, only to instantly vanish back into the void. The paradox is that if our cosmological theories are correct, there should be countless more of these isolated Boltzmann brains in the universe than there are complex beings like us with genuine histories. So why are we not one of them? This directly challenges the Anthropic Principle we discussed earlier. We use our observations of an old, structured universe to deduce the laws of physics, but if our own memories and perceptions are unreliable, then our entire foundation for knowledge crumbles. Are you a product of a 14 billion-year cosmic evolution, or are you merely a fleeting thought in an eternal, mindless vacuum, conjured into being a moment ago with the illusion of a lifetime? This is not just a philosophical puzzle. It presents a serious crisis for certain models of an eternal or cyclic universe, where such random fluctuations would be inevitable over infinite time. The fact that we observe a coherent, consistent past is a powerful piece of evidence that our universe is not a random accident in an eternal void, but has a definite beginning and a set of initial conditions that make complex, sustained structures like ourselves far more probable than a lone, hallucinating brain. The paradox forces us to confront the strange probabilistic heart of creation, where the greatest trick the void could play is not creating everything from nothing, but convincing a momentary flicker of awareness that it has always been real. This precise value of the vacuum's energy is the universe's most delicate balancing act. The energy density of empty space, the very same dark energy accelerating cosmic expansion, is not just small. It is curiously, almost impossibly, fine-tuned. If this number were even slightly larger, the repulsive force of the vacuum would have been so immense that it would have violently torn the universe apart before the first stars could ever ignite. Matter would never have had a chance to clump together into galaxies, planets, or people. Conversely, if this vacuum energy were negative, acting like an attractive force instead of a repulsive one, the cosmos would have swiftly collapsed back in on itself in a catastrophic big crunch, snuffing out any possibility of a long-lived cosmos. The window for a universe like ours, one that lasts for billions of years and allows for complexity, is unbelievably narrow. This perfect calibration forces a profound question upon us. Why is the energy of nothing so perfectly set to allow for everything? One compelling answer lies within the multiverse concept we explored. In a vast landscape of countless universes, each with its own random value for the vacuum energy, the overwhelming majority would be stillborn or fleeting. We, of course, find ourselves in one of the rare, golden exceptions where the number is just right for galaxies and life to emerge. This is the Anthropic Principle in action, a cosmic selection effect rather than a designed outcome. Another possibility is that an as yet unknown physical principle or symmetry in the laws of nature naturally forces the vacuum energy to be zero or very nearly zero. Perhaps there is a deeper law, a cancellation mechanism woven into the fabric of quantum field theory itself that we have not yet discovered. The properties of the void itself, the specific energy of the vacuum, are not a minor detail. They are as fundamental to our existence as the strength of gravity or the nuclear forces. The laws of physics provide the rules of the game, but the vacuum energy sets the stage upon which that game can be played at all. Unlocking the reason for this exquisite tuning is one of the most urgent and profound quests in all of modern science, a search that takes us right back to the mysterious heart of nothing. This invisible connection defies everything we assume about distance and separation. Two particles can become so deeply linked that measuring one instantly determines the state of the other, even if they are on opposite sides of the galaxy. Einstein famously called this spooky action at a distance, a phrase that captures the deep unease this phenomenon causes. It suggests that the space between objects, the vast emptiness we perceive, is not truly empty or passive. It is woven together with threads of instantaneous correlation, a hidden fabric of connection that makes a mockery of our classical ideas of locality. Think of it not as a message being sent, but as a single reality existing in two places at once. If you had a pair of entangled gloves and you mailed one to a friend on another continent without looking, you would not know if you had the left or right until you opened your box. The moment you see you have the left glove, you know instantly, with absolute certainty, that your friend holds the right. But with quantum gloves, the absurd and wonderful truth is that neither glove is left or right until the very moment one is observed. The act of looking itself forces the decision, and its partner, no matter how far away, instantly assumes the complementary role. This is not a signal traveling through space. It is a fundamental unity that transcends space altogether. The void is not just a bubbling sea of potential particles. It is a cosmic tapestry connected by these non-local threads. The separateness of every star, every planet, and every person may be a convincing illusion emerging from a deeper, holistic reality where everything is subtly linked. This profound interconnectedness is not just a philosophical curiosity. It is the foundational principle behind the emerging revolution of quantum computing. Where a classical computer bit is either a 0 or a 1, a quantum bit or qubit can be a complex mixture of both states simultaneously, a superposition. And when multiple qubits are entangled, their processing power grows exponentially. They can explore countless possibilities at once, solving problems in minutes that would take the most powerful supercomputers billions of years. The same spooky connection that baffled Einstein is now being harnessed in laboratories to simulate new medicines, unravel complex molecular structures, and crack encryption codes that secure our digital world. The void's hidden architecture, its web of invisible connections, is proving to be the most powerful resource we have ever discovered. It reveals a cosmos where nothing is truly alone, and where the greatest distances are, in a very real sense, an illusion. The void's energy not only built our past but now writes our future. The fate of every galaxy and star rests upon a single, mysterious number, the energy density of the vacuum. What if that number is not a constant, but a clock ticking down to an end? Some cosmologists propose that dark energy is not a static force but a dynamic field, nicknamed quintessence. Imagine this not as a fixed background energy, but as a cosmic weather pattern slowly shifting over billions of years. This quintessence field could be evolving, its repulsive power growing stronger as time goes on. In the most extreme version of this model, the vacuum energy would not just accelerate expansion, it would run away, becoming infinitely powerful. This leads to a truly terrifying finale known as the Big Rip. In this scenario, the repulsive force of the void would eventually overcome every binding force in the universe. First, galaxy clusters would be torn apart. Then, individual galaxies. As the acceleration grows exponentially, the gravitational glue holding stars within those galaxies would fail. Solar systems would be flung into the ever-darkening emptiness. In the final moments, the force would escalate, ripping apart planets, then molecules, and finally, the very atoms and nuclei that constitute all matter. The cosmos would end not with a crunch or a freeze, but with a silent, catastrophic shredding of spacetime itself, returning everything to a state of disconnected, fundamental energy. This dark future, however, is not our only path. The same quantum sea that threatens to pull the universe apart could also be its greatest gift. The zero-point energy of the vacuum represents a theoretically infinite power source, a boundless reservoir of energy shimmering in every cubic centimeter of empty space. For a civilization looking to the far future, mastering this energy would be the ultimate achievement. It would mean moving beyond stars, beyond fossil fuels, beyond all conventional power, and tapping directly into the generative hum of reality. The challenge is beyond monumental. How do you extract energy from a system that is already in its lowest possible state? It is like trying to borrow money from a bank that has an absolute zero balance. Any attempt to draw energy out would have to be incredibly subtle, perhaps by manipulating the Casimir effect or by somehow influencing the quantum fluctuations themselves. The engineering required is far beyond our current grasp, dwelling in the realm of speculative physics. Yet, if a civilization could learn to manipulate the creative power of the void, it would unlock a universe of possibilities. They could power interstellar travel, sustain habitats for billions of years, or even manipulate the fabric of spacetime. The greatest illusion, the creative nothingness from which we all came, could become our species' greatest resource, ensuring our survival and expansion long after the last stars have burned out. Our understanding of the void is no longer just a quest for knowledge, but a race for our cosmic destiny. Long before telescopes or particle accelerators, our ancestors gazed into the starry abyss and told stories. These were not just tales of gods and monsters, but profound attempts to answer the very same question that haunts modern physics. How can a vibrant, structured world emerge from a state of absolute nothingness? Cultures across the globe, completely isolated from one another, return to the same startling starting point for their creation myths, a primordial and formless void. In the Norse tradition, the universe began with Ginnungagap, a great and yawning chasm. There was no sand, no sea, no cool earth, only this immense, silent gap between the realm of fire and the realm of ice. It was within this emptiness that the first sparks of life, the giant Ymir and the cosmic cow Ordhumla, eventually stirred. The ancient Hebrew book of Genesis describes the earth as tohu wabohu, a phrase often translated as without form and void, a desolate emptiness over which a divine wind hovered. Before the command of "let there be light," there was this profound, unstructured potential. Hindu philosophy delves even deeper with the concept of Brahman, the ultimate, unchanging reality that is the source of all that is. From this singular, boundless existence, the manifold universe of names and forms is said to have manifested, a diversification emerging from an undifferentiated whole. The parallels to our scientific narrative are breathtaking. Jinngagap is not so different from the quantum vacuum, a seething gap of potential. Tohu Wabo, who mirrors the featureless, high-energy state of the universe before inflation ironed it smooth. The concept of an undifferentiated Brahman finding expression in a diverse cosmos resonates with the idea of a symmetrical, unified force field breaking its symmetry to give rise to the particles and forces we know. These myths are humanity's first cosmological models, built not with mathematics but with metaphor. They represent a deep, intuitive understanding that order is not the default state of the cosmos. Structure, life, and light are the exceptions that must be carved out of a foundational chaos or emptiness. The void was not seen as a sterile absence, but as a womb, a creative source brimming with latent possibility. This cross-cultural thread reveals that the mystery of creation from nothing is not merely a technical problem for physicists. It is a fundamental part of the human experience, a question that has echoed from the campfires of our ancestors to the conference rooms of CERN. We have always been aware of the abyss, and we have always told stories about the light that shines within it. Our everyday senses provide a brilliant but deeply limited interface with reality. You and I evolved in what the biologist Richard Dawkins called the middle world, a narrow band of existence defined by medium-sized objects moving at modest speeds. This is the world our brains were built to navigate, a world where a rock is solid, space is empty, and cause and effect follow a predictable, linear path. These intuitions are essential for survival, but they become a profound liability when we try to peer into the quantum foam or contemplate the accelerating cosmos. Our minds are simply not wired to intuitively grasp a universe where a particle can be in two places at once, or where the vacuum of space possesses a staggering intrinsic energy. This is not a failure of intellect, but a consequence of our evolutionary history. Our cognitive biases are like a pair of glasses perfectly tuned for seeing trees and predators, but they blur and distort when we try to observe the atoms of the tree or the curvature of space-time itself. We instinctively seek concrete causes and solid objects, which is why the probabilistic, wave-like nature of quantum reality feels so alien and unsettling. The very idea that a particle does not have a definite location until it is measured clashes violently with our middle world experience, where a stone exists in one place whether we look at it or not. Our language itself betrays this limitation, forcing us to describe the indescribable using metaphors rooted in our familiar scale. We speak of strings vibrating or a quantum foam, but these are just clumsy analogies for a reality that has no direct parallel in our daily lives. This necessary humility is the engine of scientific progress. Every major leap in physics has required us to abandon a common-sense intuition. We had to accept that Earth is not the center of the universe, that time is not absolute, and that solid matter is mostly empty space. Recognizing that our perception is a useful illusion, a simplified dashboard for navigating a much stranger reality, is the first step toward a deeper understanding. It prepares us to accept that the universe's greatest trick is not just the creation of everything from nothing, but the fact that this magnificent truth is hidden behind the very interface of our own minds. So the grand tapestry comes into view, a single, shimmering whole. We have traveled from the fleeting dance of virtual particles to the vast architecture of galaxy clusters, all seemingly born from an emptiness that is anything but empty. The ultimate illusion is not merely that something came from nothing, but that the solid, separate objects we perceive exist within a passive void. The truth is far more radical. That void is the primary reality, a dynamic and unimaginably energetic field that serves as the ground of all being. What we call a particle is not a tiny billiard ball but a localized excitation, a temporary knot of energy in this universal medium. Space and time themselves may not be fundamental, but instead emerge from a deeper, more abstract network of relationships, like the smooth image on a screen emerging from countless tiny pixels. Our entire cosmos, with its billions of galaxies and its arrow of time, could be a magnificent hologram, a three-dimensional projection of information encoded on a distant, two-dimensional surface. Or it might be a specific, self-consistent mathematical structure, one of countless perfect forms in a Platonic realm of pure logic. This unified perspective dissolves the hard line between nothing and everything. The transition is not a singular, distant event in the past. It is a continuous, ongoing process woven into every moment and every point in space. The quantum fields are constantly humming, the virtual particles are forever flickering, and the fabric of space-time is continuously being woven from the bottom up. This is not a cold, mechanical universe. It is a living, breathing reality of unimaginable elegance and mystery, a cosmic dance where the dancer and the dance are one, and where the greatest magic trick of all is the breathtaking illusion of a solid world emerging from a creative, vibrant, and boundless void. Our journey ends not with a final answer, but with a new way of seeing. We have ventured to the very edge of understanding, where the solid ground of classical reality gives way to the quantum foam, and where the silence of the void is revealed as a symphony of creation. This exploration has unraveled the universe's greatest illusion, showing us that the vacuum is not a barren emptiness but a fertile ground, a dynamic plenum humming with potential. From its fleeting quantum whispers sprang the particles that built atoms, the forces that sculpted galaxies, and the improbable conditions that allowed life and consciousness to blossom. This knowledge fundamentally challenges our deepest assumptions. We are invited to stop seeing the cosmos as a collection of isolated objects drifting in a passive container of space. Instead, we can begin to perceive it as a unified, dynamic whole, a magnificent tapestry continuously woven from a deeper, hidden foundation. The separateness you feel from the screen in front of you, from the air you breathe, and from the distant stars is the most convincing part of the illusion. In truth, we are all temporary excitations in the same cosmic field, intricate patterns in a single, unfolding reality. So the next time you find yourself beneath a clear night sky, gazing into that profound darkness, remember this. You are not looking out into a cold, passive void. You are peering into the vibrant source of creation itself, the same generative ground from which you yourself emerged. If this perspective has shifted the way you perceive your own reality, even just a little, we would love to hear your thoughts in the comments below. Subscribe for more journeys into the heart of cosmic mystery, and please, never stop questioning the beautiful, bewildering nature of everything.